homotopy theory. Um, okay. Actually, there is. Is it readable? Hi everyone, is it readable? Or should I write a bit larger, actually?
Looks good to me.
It's fine, yeah.
Okay. Maybe a bit larger, but okay, the title is here. This is a paper titled exactly this by Daniel Duggan. The reason I want to talk about this is because we are doing homotopy theories, and there are two major things that we should care about. One is like, why do we care about motivic homology, motivic homotopy theories? That is something I can't answer, and I don't know where to go. I don't know what's the fundamental problem. I know the fundamental problem, but I don't know how to answer it. The other thing is like, how are motivic homotopy theories and motivic homologies related with other things? And this will be telling you one aspect of these things, like how this will be an example of the universal homotopy theories here. And you will see, like, under this framework, it will be like connecting with other things pretty easily. And this is a very readable paper. I suggest that if you are interested in it, please read it. I'm going to talk about many things, and not all of the things, but the major point at this one, we will conclude that the motivic homotopy theory is one of the major examples that in the universal homotopy theories. This is done actually by model categories. And it's kind of a trend that whenever you have a model category, you want to find if there is an infinity category. Could be like modeling your model category, and somehow people are trying to translate all the things in the language of infinity category. And if you are interested in this part, I feel like this is one of the things that I'm most interested in to discuss. And if you want to do it, then let me know, and we can have some have some details in the we could discuss some details. Okay, so what are we going to do today? The goal is to say given a model category, can we give it a presentation? What do I mean by a presentation? So for algebra, the presentation is kind of like very simple. If you have an algebra, then the presentation should be you have n many generator and you have p many relations. So this is a presentation of algebra. Similarly, if you have a Lie algebra, then you could also have you have a 3D algebra. Then you quotient out by some relations as well. Then now, given a model category, can we do this as well? In general, no. But if you impose some good, but not very restricted conditions on it, then you are able to do this. And how do we do it? How do we do it? How do we present a model category?
Before you proceed there, I have a question. So,
Yes.
why would
someone like as a homotopy theorist would care about a presentation, like
Why don't you care about presentation, for instance?
uh,
So if I say, how do you describe the homotopy? How do you describe the Kohn model structure on the category of topological spaces? Why do we care about this thing?
okay.
So yes, so giving a presentation is like describing it instead of using so many words, but you do have you sort of know the generators, you sort of know the relations, and you
Mhm.
easily see that these relations, this all of the relations are the thing that you want to impose, saying that these are the weak equivalences. What kind of weak equivalence do you want to study?
Okay, I
So
see.
in,
I
in
see.
that in that thing in top, the relation is a weak equivalence. So we homotopy equivalence. We really want to impose this thing on it so that this category with this model structure should be the one that we care about. And it has a very good presentation in this sense. Good? Do I answer your question? Okay. Now, how do we present a model category? You need generators. I will call it generators, which is a small category. We will denote it always by C and some relations that you want to impose on. Okay. All right. These are the big picture, and before that, any questions? Any questions? Good, good. Now, before we really go to uh, model categories, I want to give this example that um, um, how do I, what do I mean by a generator is a small category? So, running example. So you could always think that the small category is the category of delta, which is the category of simplices. And you have a geometric presentation, which is one point, the interval, triangle, all of the things. Keep going, and you have so I'm gonna this way. 1, 2, 3, 1, 2, 3, 4, and also backwards. Things going on. Yes, this looks like very nice, but the problem is like we can't even have cannot have a very simple thing like S1. So how do I get a circle out of this category? You can't do it because they are not so. These things are so rigid, because this category is very rigid, we cannot really have S1 out of this small category. Now, how do we fix it? Uh, I will quote unquote uh, formally add uh, all colimits. All colimits. So what do I mean by this? For instance, what is S1? S1 is you have two dots and you have one interval and another interval. Two intervals, if we glue them along only this, then you have this. You have the circle. You have S1. So to have S1, it's nothing but you know how to glue things, and glue things is taking union. And taking union is nothing but do the colimit, and this is how to fix it. Now, how to say it in math words? Proposition. Okay, I'm gonna erase this for the moment. So S1, I'd say S1 is I is joined union with I along S0. Okay, so the proposition says this. For any so complete category D, then we have this diagram C, and okay, and for any functor up from C to D, then we have this diagram. C goes to D, and we have the unit of embedding. I will denote it by H, and I want to point out that this H in Dagger, it's small r. It's always small r. Okay. Unit of embedding is embed your category into the category of pre-shifts over C, which is all the functors from C off to set. Okay. So if you have this, the magic shows up here. Then you will automatically have such a functor. I will call it realization, and natural transformation, which is initial, which is among all such pair. Functor with a functor with transformation. So this is a realization, and you also have sort of the inverse, which is called the singular complex functor from D to pre-shifts, so that this is a pair of junction. Any questions about this abstractness?
Yeah, what is the other functors? So
Realization. The other one is singular complex, SING. Okay, so I will explain these two notations a little bit after, but you will see why it's looking like this. Okay, let me give you this example.
Hey, before you move on, so this is Daniel Dagger's proposition that.
No, well, yes, no. Proposition 1 in Daniel Dagger, but it's not shown by him. It's a well-known. It's a sort of like a well-known thing.
Ah, okay, okay.
This realization is the left arm extension. You could say that you could just say this is a colimit of something. So whatever. This is a left arm extension. So you have a lot of ways of presenting it, and because this category D is co-complete, you have like a lot of good things happening. Like this is already a pointwise left arm extension. Okay.
Got it.
So example that I promised. Okay, so let's just say this category could be the category of simplices, and it's mapped into the pre-shifts on it, and the pre-shift is nothing but simply short step. Now let's construct another functor from delta to the category of topological spaces. Now, what is this functor? Okay, this functor is sending n to the geometric complex. No, it was simplex. Sorry. This is the geometric simplex, which is denoted here. So these are topological spaces. Now, I do have such a pair, and one is from the pre-shifts to the target category, which is co-complete, re, and the other one is backward and in. Okay, what are these functors in this situation? Nothing, but this is the realization, and this is taking the singular complex of a topological space. You have actually nothing, but like your geometric realization is only a simple application of this proposition. Any questions about it? Good? Okay, very good. I really want to point out that this example, this wrong example, you should always keep it for reading this universal homotopy theory. Like this is the fundamental everything that basically all the things comes from here. Okay. Any questions? Any questions? Okay, very nice. Good, good, good. So this is some abstract things, but you see like the application is very nice. Well, the problem is like I do have such a co-complete category D, but this D here I didn't impose any like model category on it. The next step is really like really extend this proposition one a little bit more so that this has this category target category D has some model structure on it. Let's do it. So I'm sorry, I do not have so much space, so please keep this example in your mind. This will help you understand almost everything. Okay. Proposition 2. Now, for any model category, now I do not need the co-completeness because every model category is required to be co-complete and complete. This is basically a lot of time that a category is not a model category. When that happens, you know how to fix it. Just formally add all the co-limits like just as in proposition 1. Okay. Then for any model category, um, and a functor. Let me make sure that I'm stating the correct things. Oh, yes. I forgot to point out that this factor, this factorization is, this factorization is unique up to uh, a unique up to a unique isomorphism. Is that the correct way to say it? Yes, unique up to a unique isomorphism. It looks weird at the beginning, but I don't know if I have time to really talk about it. But this is really saying that factorization, if we make this as a category, then it's a contractible group point, something like that. Okay, so now we are ready to talk about it. That any functor from uh, a small category to a model category, then we still have this diagram from the small category to model category. Then it needs to factor through some universal homotopy theory on, on C, so that you have a realization and where's my blue? Singular complex, this kind of thing. Here, then there exists this universal homotopy theory and a pair of a Quilling pair. Okay, a Quilling pair RE and thing and a natural transformation from RE composed with Yoneda functor to your okay, and important thing that this transformation is always a weak equivalence, natural weak equivalence. Okay, now the problem may be, what is the construction on this model category? Now, luckily I still have proposition 1. So, what is the idea of proposition 1 to have such a thing is that like this category, this co-complete category D is constructed from C, adding all formal colimits, and then quotient out something. So this is the idea. You have your generator, you have all the colimits on it, and then you quotient out something to get D. Now, here I not only I have this functor, but also I have some extra structure on the category M, which is the model category. So in this time, I do not formally add all the colimits. I should something like add all homotopy colimits. So if you add all the homotopy colimits, then this should be the thing that you have. Now, what is like the mathematical language to do this? It's not very hard to guess. It's just the simplest of free sheaves over your category C. Now, the next step is what do I mean by homotopy colimit? The meaning here is that there is a model structure on this simplicial preshift of this small category C, which is called the projective model structure, which is sort of like the universal one in the sense that I just wrote. So our target at the very end should be like all the other model categories, if we impose on some conditions on it, should be coming from such a universal. And that's what we say a lot of things. So this projective is also called force field on model structure. This BK. It's cofibrantly generated, it's broken, and there are a lot of good things on it. And it's also a simply short model category. So there are so many good things happening here. Okay, any questions? Any questions?
I'm good.
Let me give you a trivial example first. So, if you take C equals to 1 point, then nothing inside it, then UC is nothing but simply yourself. Well, this is so trivial that it looks silly at the beginning. Later on, we will talk about more things.
Yeah, sorry, can you explain why this is the simplicial set, UC?
So let's see. What is the simplicial presheaf over a category with only 1 point?
Oh, simplicial presheaf, not actual presheaf. Yeah, that's a simplicial.
No, it's more than actual presheaf. It's
Yeah,
much
yeah, yeah,
more
yeah.
than actual
So,
presheaf.
so by simplicial presheaf, you mean all the functors from C op to simplicial sets,
Yes,
right?
exactly.
Okay.
Exactly.
Okay.
So this is not simplicial. This is not presheaf, but simplicial presheaf. Some technicality that I do not want to really get into it is okay. You have a calculation of the left Hahn extension, which is can I remember it correctly? I don't know. So C over F probably is up to yes C over F. Then you have H composed with P. Yes, this will be sort of a presentation of your left Hahn extension. So it's a colimit on the category of C over F, this common category. And why do we care about it? Because like this C over F category will give you a lot of cofibrant object in the category of simplicial presheaves over C. That's something technical I do not really want to get into, but I want to mention that you have different ways to get a cofibrant replacement of an object. Let me translate again. You have a way to get a good projective resolution of your object. So that's why this Bose-Field-Kahn model structure is a little bit able to handle. Any questions? If not, I will have to like erase proposition 1. Okay. Second example. Of proposition 1, but not proposition 2. Okay, so now I still have this category delta, which is the category of simplexes. I have a unit and embedding into some functional set as usual. Now, this time I'm not sending it to topological spaces, but I'm sending it to the category of small categories, where you send n to be the category looking like you have an object, n plus one object, and n many arrows, n many distinct arrows. So this is certainly a category inside it. Do we buy this? Now I'm going to show another magic here. We have two pairs. This is the realization, and this is the singular complex. Now, what is the realization here from a simplicial set to categories? Now let's talk about singular.
Isn't that nerve?
No, the other way. Singular is the nerve.
Oh, right.
It's the
Singular.
nerve of some category. You're very correct. The other one is called how one is the Thomason's sort of Thomason's construction. So what is tau one? Okay, what is tau one? I have sequential sets x0, x1, x2, x3, and so on. So objects are all x0s, so these are the objects. X1s are the morphisms. And x2 tell you how to compose morphism, which means that if you have such a thing where you have such a two simplex, then this F composed with G is this H. This is telling you how to compose morphisms. Now, we know what are the objects, we know what are the morphisms, so we have a category.
I mean, this wasn't anything special, right? I mean,
what do you mean by this?
It does not like deserve a special name saying Thomason construction or something like that. That's what I'm saying.
No, well, it was discussed in Thomason's thesis, actually. Originally, yes. No, well, the problem. No, you feel like it's a bit silly, right?
Yeah, exactly.
We only used up to x2. This is not a reasonable thing at all. This is not a reasonable thing at all, I want to say.
Okay.
So that's the problem. When you throw everything here, that this all the high information are thrown away. It shouldn't be like such a thing. Now, this is a little bit digression, but how to fix it? Fix it is you have simplicial sets, you have simplicial categories instead of categories, but you have simplicial categories. Now, remember that this was nerve. Now, this nerve should be changed to another thing which is called the coherent node of a simplicial category. Now the other way is left, right, C. I can't remember what the name of this thing. So instead, now we do not have any what to say, like this is not the Kling-Kong model, but the Joyol model. If we have the Joyol model on it, then this will be a Kling equivalence. Like you want the really the way to fix, like we throw all the high information, is that we shouldn't have categories here. This category has its own problem on it, because all the category, if you take the nerve, it's this thing is what's the name of that? What's the name of that? It's two co-skeletal. All category are two co-skeletal, which means that all the higher things should be thrown away. This category has its nature to be a bad thing. Doesn't behave well, so we need to change it to be the category to be simplicial categories. Now, these two things will give you the great models of infinity categories. Anyways, that's not the target today. I just want to mention that this example, why do we care about it? Because like it gives another way to go other places to discuss infinity categories. Okay. Now, I do not want to erase my proposition, so remark. Remark one is there are good ways to find covibrant replacement level. I've talked about it. Just want to write it down. The second one is this universal homotopy theory is essentially the same as co-simplicial resolution. I can talk about it, but I do not have so many time, and this seemed to be a little bit, how to say, a digression. But I still want to mention this because there are other points of view that we could use to say what this universal homotopy is. Okay. Now, why do we care about this? Because this gives a way to express homotopy colimit, which is always what we want to see. Remark 3 is we have a dual notion. Sorry, we have a dual mean of C. Here you have like all the things are sort of, this is initial, but in the dual sense you have target. This will be a terminal thing, and that will be the simplicial resolution, and this gives a way to express homotopy limit. So you do have a way to like swap all the direction of your arrows, and you can talk about it as well. So it's not there is a dual notion, and we will always use this colimit version. We'll always like care about homotopy colimit. You will see why we are doing this. Any questions? Okay, good. Now let's go back to see proposition 2 again. That I haven't really say. Okay, I did say that this is a Quilling pair. So this is a Quilling pair, but this is not always a Quilling equivalence. So what what is the problem here? Let's try to see something.
Sorry, I think I might have like forgot what's the difference between. I mean, I know what a Quillian equivalence is, but what's a Quillian pair?
Oh, quantum pair is saying you have many uh, equivalent definitions absent uh, co-fibrations and acyclic co-fibrations to O5 and acyclic O5, or G send fibrations to fibrations and acyclic fibrations to acyclic fibrations, or similarly other things. So, okay, you remind me of saying something that's remarkable. The correct way is this. A quantum pair is an arrow from M to N um, if M states start from left in your quantum pair. So an arrow in homotopy theory is not a functor, but a pair of functors.
True, but what is a Quillian equivalence then? It
Quantum
means
equivalent
that.
is more than this thing. So this is only saying, okay, how to understand this thing. This always say, okay, F preserves the resolutions. G preserves the resolutions. Okay. Now, quantum equivalence says that F, if you have F from a cofibrant to cofibrant again, and this is a weak equivalence, then F of F is still a weak equivalence. So let me use another way. So if you have F from M to N, then we, after localizing it, we have O of M and O of N left the right functor and the right functor. So a Quillian pair means that you have a pair of a junction on the level of localizations. You do not know more. Now, Quillian equivalence says that this pair of junction
Gotcha. Yeah.
is a equivalence of categories.
Yeah. True.
Okay. Good. Now, we're really getting to the core of many things. So, important example. This will be changing it a little bit, but we have delta from okay. We have delta from this geometric thing from category simplices to top, and we also have this unita embedding instead to simplicial set, but bisimplicial set, which is simplicial spaces. Okay? Now, we map our delta into the simplicial preshapes over delta, Now you have two deltas as your parameter. So this is a bisimplicial, the category of bisimplicial set, and we know that we have this realization and singular bicomplex. Now, for bisimplicial set, okay, so this realization is sort of the realization that you want, but again, this pair junction is not a Quilling pair, which means that this simplicial space is not really what we want. That carries out the model structure, the homotopy theory that we care about on topological space. Why is this thing happening? So, question: the problem is that delta n, this thing inside your bisimplicial set, is not contractible yet. So if you don't have any other things inside this, you see inside your universal model category, you don't have like delta to be contractible, and this will be your problem. Now, how to fix it?
Sorry, I don't understand why it's not contractible. Like,
You do not have any things like, remember, what is the projecting model structure on it? It's on every object that something happens. So
yeah,
this is like every object. Now you don't know on this object it has any other relation with delta n minus 1, for instance. But these two need to be equivalent, right? You see it?
yeah.
Because this is too universal. It doesn't have this relation. Now, again, how to fix this problem? But before, we don't have so many homotopy colimit. We impose the homotopy colimit inside our account. Now, this time, we don't have so many relations. We impose the relations on it. So how to do it? Now, this is a thing called field localization. And I have talked about it, we have seen it. So this is saying we are adding some more weaker cornices on it by doing the as local things as we did before. So I'm not going to write the proposition because I'm a bit running low of time. But I want to say that here, this is the only problem. If you impose the condition that all delta n to be contractible, then bisimplicial set with your new model structure is equivalent. Is a category which is equivalent to topological spaces. So this is one example that before we do not have so many things. We can't have the spaces, so we impose homotopy colimit on it, and then we see that this is not really what the model category that we want, so we impose relations on it by using most field localization, and it is getting us the thing that we want. Okay, any questions? So, in conclusion, I waited so long before I erase this part. Now I think I'm good to say it. So um, let's say simple space with the universal and imposing condition that all simplices are contractible, then this is equivalent with topological spaces, and this pair is given by is induced by our realization of singular complex, given by the diagram that I just erased. So, okay. What your takeaway is that for model category to compare, so if you have a pair of you have a Green pair of junction that preserves something, then it induces by force field localization something which is called quotient out bias, which is actually should be say localized at us such that if you do the correct choice of us, then this is by putting equivalence if S is cleverly chosen. Okay, any questions? Now it's very close to I only need one more piece to talk about things. Okay. Peak condition. So what do I mean by shift condition? I will mostly we can suppose C and how this is a site, which means that this is a category with a Grothendieck topology. Now, a sheaf um, is a functor from C to the category set, such that you can such that you can glue from local to global. I don't want to write the actual conditions what they are. I can, but I don't want to do that. Now it's sort of looking like you have something like this, and then if this is a co-equalizer, then this is a sheaf. Like this co-equalizer comes from this diagram comes from your topology. Now, if we say a bit more, a stack is a second version of it is quote-unquote functor from the category. Now you can't have set because you erase it. This should go to the two category of group point, such that you can glue from local to global, not only on object but also on morphisms. Again, thanks. Now, if I use some other thing, then it looks like something like this. This is basically saying a stack is a raised, a two categorical version of your sheaf. Now you have more technical things to really say what a stack is, but the point is like, now if we don't have this, it looks okay because like a co-equalizer of this thing really means something. That's a special thing that you care about. But now this is like this is stupid truncation. This is stupid truncation that you really should have all the things going up instead of truncated at the level of 2. Now, so another bullet is a hypercolor is a functor. Again, I have to code it, a functor. Instead from C2 set or group point, now I need make this not only a 2 category but infinity thing. So this should be going to simulation group point, or I would call it animation or any other things. Like you just think that this sort of like the topological spaces that carries out all the high information. Now, it's a functor from C to some infinity category such that you can glue things from local to global, not only for object, but for morphisms, 2 morphisms, 3 morphisms, and so on, which is exhibit at like this thing. So if the homotopy colimit of this guy is your thing applied on it, then it's a hypersheaf. It's a derived stack. So a hypercover is all something like this. You could well, it's not a good thing, but say it's the same as an infinity stack.
Sorry, just to make sure that I understand it correctly, your sheaf is a co-equalizer of just, first 2. Yeah.
Sort of yes. Sort of yes.
Yeah. For stack, you are going to the 3rd level.
So
yeah.
Sheaf is saying, okay, you can, if you have a function on each part, then there is a global function which restricts onto each part.
Yeah, that's what this.
Okay. That's a sheaf. Now, stack is not only on functions, but functions from function to function. So you have raised
That's
it.
going to the 3rd level.
Yeah. So
and you're saying that hypercover going to everything.
Yeah, going to everything. Yes, exactly.
Okay.
So I didn't give you the actual definition. No, it's way too much to give it to you. But no, this is how you should think of it. Like what a sheaf is, what a stack is, and what a hypercover is. Like this is the modern point of view. Now, okay, why do I need to talk about it? So, we are really close to our final goal. As I said, I only need this part. Okay. Say, suppose see how this is a type, and you see over how this was your universal homotopy theory, and this is the localization. Localizing is the model category. Localizing. Localizing means imposing relations. Localizing at the subcategory which is generated by all hypercolors. So what do I mean by this? I mean if um, uh, what do I mean by this? Uh, if I have sort of a thing, okay, I will call it U star X. If this is a hypercover, then I would say that this too will be giving me the same. This too gives the same uh, object in the model category, in the homotopy theory. So, I mean, if I have a cover of your space, a cover of your space is the same as your space. There is nothing different. So here, this is only saying this model structure is given by your relations, and the is given by your generator C, and the relations imposed on it are nothing but your hypercovers. Hypercovers are nothing from your graphenic topology. So basically, like how to glue these things together to discuss something. A very important thing. Okay. This map from you see over the tau to simply show three sheaves on this category with Jardine model structure is according equivalence. Now, the Jardine model structure on simply show three sheaves is the same as your universal structure imposing some other things coming from the topology. So I do not have any time to talk about this, but I want to say, okay, this is really something other people cared about, and Jardine model structure is basically like the most applicable things. Okay, finally, we go back to motivic. All right. So we have our category C to be the smooth varieties over C, and we have um, well, the same as simply show sheaves of so this simply show sheaves over smooth over K with Alvey model structure is what we have seen in the notes, right? So this is the thing. This is the thing. Now, how do we? I will just call this. I will just call this category to be Alvey. Stand for Moron with this. So now we have U of smooth. Okay, this is the universal homotopy theory on smooth varieties over K. Now, there are two things we want to do. The first one is, okay, hypercovers. So that one coming from this theorem. Okay. The second one is, okay, for any variety between crossed with a one, and this should be the same as your original one. So I will call this this U localizing at 1 and 2 to be U of smooth over K with A1 relations on it. This is a model category coming from the universal homotopy theory by adding one coming from hypercovers and second coming from A1 relations. Now, claim. This is equivalent to V over K, which is what we have seen from others. Okay, so what do I mean by this thing? I now give V a presentation where the generators are the smooth schemes and the relations are hypercovers and A1 relation. Why do we do this? Why do we do this? Why this is helpful? Like let's go to so somehow this is a little bit more handleable because when K equals to, for instance, when A equals to R the real numbers, then smooth over R is nothing but manifold. Now, if we have this and imposing the A1 relations, now this is nothing but your topological spaces. You again go back, you really go back to the original homotopy theory that we care about to compute the homotopy groups of spheres. So this is more handleable in such a way that we can see why this Lewandowski-Morel motivic model structure is sort of like useful, and that's probably the reason why am I correct that Professor Hoffman provided some notes pretty long, but there are some applications of a motivic to compute the homotopy groups of spheres, right? So I believe this call could be give you a reason why this could be happening, because when K goes to R, then we do have this chain of equivalences go back to the original homotopy theory that we came.
Yeah, I'm totally shocked by the discovery. This is a result that came out either this year or last year. It's a huge paper in the IHES publications, the top journal in the world, 100 pages long. And they pushed the computation of the stable homotopy groups of spheres from 60 to 90. They'd only been able to compute up to 60. Now they can go all the way up to 90, but they're using ideas from the motivic homotopy theory. Somehow or other, they can relate these two theories. I frankly do not understand exactly how they're related, but it's mind-blowing that you can actually use this to gain new information on a very, very classical subject like homotopy groups of spheres.
That's
Right.
dope.
Who knows what, other,
Amazing.
other homotopy, other functors, cobordism, whatever, who knows what other insights you might gain by using these methods.
So
It's
can you tell me
very
who
exciting. I
published the
mean,
author?
what?
Sorry, who published that paper? The IHE
Four
something?
authors.
IHES,
I just know
3 or
one.
4 authors, 2 of them Chinese, by the way.
Yeah, Zhou Lixu. I know this guy pretty well. Like I've seen a lot of his work through the computations of.
Is he's the one at Fudan, or is the other one at?
Yes, yes. The other one, the other one. He's somewhere in California, if I remember it correctly. But he has a really deep connection with Fudan.
It makes heavy use of machine calculations as well. But the shocking thing to me is that these motivic things are actually computable, and they can actually use those computations. Don't ask me exactly how, to gain information about the stable homotopy groups of spheres. And by the way, this also has to do with smooth, these famous examples of Milner about not, you don't have unique smooth structures on spheres.
I see.
And
S7.
Hervé and Milner had related these to stable homotopy groups, and apparently this answers new questions about spheres, just ordinary topological spheres. So incredibly, this machinery is actually being put to use in ordinary topology. It's amazing to me. So I think this is exciting mathematics. Well, that's all I can say.
Okay. Yeah. I think I'm gonna end it here as well. So like
Okay.
the whole topic is like given any good model good model category. Well, I didn't talk about the name, but it's combinatorial. If the model structure is combinatorial, then you have such a presentation. And Amway is combinatorial, so you do have like this whole machine. First, like it looks like just some abstract, but after seeing some example, I do believe that you should say like, okay, these are good mathematics. Anyways, I like this paper pretty much.
Right. I think, anyway, thanks for the lecture, and
Thank you for listening.